right. So, this is clear, right. I mean, what happens in case of sliding friction, all right. Now, in metal cutting, the coefficient of friction can vary considerably along the chip tool contact length on the rake face. That is between the in the contact between the rake face and the chip, all right. Now, this is because it results from very high normal pressure that exists at the chip tool interface. Let me explain it to you. I already told you that maximum stress happen, maximum strain happens at the tip tool, right. And I have shown you the normal stress curve. It reduces along this. So, since at the contact point the maximum strain happens, that is strain rate or strain because of the maximum pressure, okay. This is what happens, okay. The real area of contact becomes almost the same as the apparent area of contact, and this high pressure remains not throughout, but up to some distance, up to some length of the chip in the chip tool contact length. After that, the pressure is relatively less, okay, and at least this thing does not happen, all right. So, let me explain it to you here. Okay, in this case, if you see the sketch here, this is the tool, all right. This is the tool, and this is how the chip flows along the rake face of the tool, all right. Now, the normal stress happens to be of this nature, all right. Because of this, let us say along this chip tool contact length, let us say this is the length, from here to here the force is so high, pressure is so high that the apparent area of contact becomes equal to the real area of contact, meaning that all the asperities get deformed plastically absolutely, and both the areas become the same, all right. Now, the remaining portion from here to here, all right, the pressure is less, and therefore, the sliding friction phenomena takes place, meaning that there the mu remains constant within that. Here the mu remains constant, we said that, right. This is because not all asperities get flattened, let us say, in one word, okay. So, this is exactly what happens in this area. Now, within this chip tool contact length, the area, the length where the normal force become very high, that is actually called the sticking zone, and the zone where the mu remains constant, that means not AR is not equal to AA, that zone is called the sliding zone. So, in the sliding zone mu remains constant, and in the sticking zone the mu does not remain constant, all right. So, therefore, what happens is this: if we draw the friction force versus the normal force curve, within a certain length where the normal force is within a limit, okay, that means not very high, from low to medium or normal, it happens to be the mu is equal to constant within that length, okay. But after that, as the normal force is going higher, AR is becoming, real area of contact is becoming the same as the apparent area of contact, and mu does not remain constant anymore there in that length. So, in that case what happens that within without any change in the friction force, okay, the friction force remain constant, and the normal force and friction force, they are not equivalent, I mean they are not proportional, because the mu is not constant. So, therefore, it remains almost constant, I mean to say the friction force almost remain constant. F is now independent of n in this case, and the ordinary law of friction no longer apply. Under these conditions, the shearing action is no longer confined to the surface asperities. Okay. if you remember, we said that in case of sliding friction, the surface asperities as they get welded, with the shearing action, I mean with the movement, it is being sheared. Now, when there is a movement here, the shearing action no longer confined to the surface asperities, but it happens from within the softer workpiece, softer material, okay, body of the softer metal. Let us see the model, what we talk about the model. Okay. The model is that if we assume that this is the length, and let us say that this is, we will imagine, we will find out this length, let us say up to this length, from here to here it is the sticking zone, and from here to here it is the sliding zone. Now, we know exactly the point where the chip leaves the contact with the rake face. Okay. So, that point is, let us say x is equal to 0, all right, and x is increasing as this length is increasing, all right. You understand? X is equal to 0 at this point, and x is equal to, let us say LF at this point. This is a maximum. Okay. This is, let us say LF distance, and this is the distance which we will designate as the LST, sticking zone, all right. Now, the normal stress distribution on the tool face, this has been assumed to be in the, this is the curve. So, this has been assumed to be in the form of q x to the power y, nonlinear one. Okay. I mean, this is the equation of this curve, let us say. Now, we will find out that what are those parameters. X, as we said, this is the distance where the chip tool starting from the point where the chip leaves the contact with the rake face, okay, and this is in the increasing the value up to the tool tip. Okay. Q and the y, these are constants, let us say. Now, the sigma f is the normal force, so normal stress. This will be maximum where the x becomes LF, right. So, in that case, the sigma f maximum can be written from here is that q x become LF to the power y, right. From here, we can find out this constant value q, which is sigma f max divided by L f to the power y, that is L f to the power minus y. Okay. Therefore, we can find out that the sigma f, if we put the value of q here, it will be of this nature, right. In the sliding region, look at the sliding region, it is here, where that is x equal to 0 to x equal to LF minus LST within this length, all right. Within this length, mu is constant, we have said, because this is the sliding friction condition, and the distribution of shear stress, okay, this curve is given by tau is equal to sigma f mu, right. Sigma f we have, and that if we multiply by mu, this will give you the, mu is a friction coefficient, right, coefficient of friction, that will give you the shear stress, all right, and that is equal to sigma f, you put this value, it will be this one. Therefore, we are saying that since this is the nature of the tau, so the curve will be like this. Okay. Let us say this is the equation of this curve now, all right. Then what happens that in the distance from here to here, that is x equal to LF minus LST to x equal to LF, in here what happens, this is the midpoint where both the stresses meet, right. See this? Okay. Here the shear stress become maximum everywhere, all right. You understand why? Because here we said that this is the sticking zone, all the asperities get plastically deformed, AR is equal to AA, so shear stress is maximum, all right. Let us say this maximum shear stress is tau st, we will designate it by tau st, okay. This is the tau st. Now, if we integrate now this sigma f from sigma f value, that is from 0 to LF, okay, here, then what we will get is the normal force, right, because it is a sigma sigma f that we are integrating from 0 to LF. Okay. So, we are getting the normal force, normal force. So, this is the area into stress. It will be, if you integrate this, this is we are taking as sigma f, which is sigma f max x by LF to the power y, that we have already found out, and that is the result, sigma f max AW LF, this is the area 1 by 1 plus y, okay, divided by 1 plus y. If we found out the normal force this way, the friction force can be found out by integrating this, right, okay. And this we are finding out, we have the previous one, okay. Like what we are doing here is that we are taking this component and this component. This component is this one, this component is that, okay. You understand that? We are summing them up and we are saying that the friction force F along this length can be found out by this way, okay, by combining this portion as well as this portion, that is sticking zone as well as sliding zone. If we integrate that, it will be like this, okay, the result. Now, this is very difficult to handle, as we can see that there are many components which will be unknown, all right. Let us simplify that. As I was telling that this is the junction, this is the point where the sliding and the sticking zones meet. There we have two conditions. For example, at this point, okay, we have normal stress given by tau st divided by mu, okay. Oh, sorry, we have that before. At this point, we have the tau st divided by mu, which is the normal stress at this point, isn't it? Agreed? Tau st is here, okay, divided by mu will give you the normal stress. However, the normal stress from here at this point you can compute by this formula, sigma f equal to sigma f max we have already determined. Now, what happens is that x only thing is that is becoming LF minus LST, right. If you put the x is equal to LF minus LST, then we will have the normal stress at this point as long as this curve is concerned. Agreed? So, what we say is that at this point we have this and this values. So, they will be equal, okay. If you multiply by mu, this will be the shear stress, all right, because this is equal to mu tau st divided by mu. So, tau st will be mu into this, because this and this will be the same, they are at this point. Are you with me? Is it clear? Okay. So, if you do that, then you substitute this equation into the equation that we have derived here. See that these parameters are coming, all right, and then you can simplify that. You put this equation there and you simplify that. Now, the mean coefficient of friction on the tool face can now be expressed as Ff divided by Fn, okay, F by n overall. Mu is equal to F by n, which is tan of the friction angle, that is what we are talking about. Ff we know, Fn we know, okay, previously we have done. So, this is becoming very simple formula like this, all right. Now, the mean normal stress on the tool face, this is given by this Fn divided by Aw, which is the area, and the Lf, okay. N, because we said as the, if you remember, we have decided, we have derived this formula, right, that we are integrating the normal the area we are taking by integrating the equation, and we are taking the normal force, okay. So, because of that we will have this formula, that this is given by Fn divided by AWLF. Okay. This is it clear to you, all of you? See, what we are talking about is that okay. Let me clarify one thing, because this may be little confusing. See, this is clear, right? The average normal stress can be given by normal force divided by that area. Okay. Now, Fn is actually the same. This is written in a different way. This is the normal force. Here it is designated as Fn, here it is N. So, let it not confuse you. This is the same thing as Fn. So, if you put this value, okay, you can see that AWLF will be cancelled and it will be sigma F max divided by 1 by y. Okay, this will be cancelled because this Fn will be on top and AWLF will be on both sides, numerator and denominator. Okay, this is clear. If you are taking note, just make sure that Fn and N, these are the same thing, it is a normal force.
What is the AWF?
Is the area.
And LF is?
LF is the, it's actually the width. Width and L makes the area.
Okay, so AW is the width, right?
Yes, AW, see, no. Yeah, this is, please don't get confused if I said that AW is the width and LF together, product of that is the area. Okay, so F by area, force upon area is the stress, all right. Width and length will give you the area. Okay. All right, so we are getting that sigma F maximum from here, 1 by 1 plus y and the Fn, okay. And therefore, if you substitute the sigma F max, okay, as we have taken in here, okay, then what you will be getting is the beta is equal to arc tan of this. So, here what happens is that normally experimental works have found out that this factor, okay, this factor 1 plus y into this by divided by 1 plus y, this remains reasonably constant. Okay. This is experimental works have shown, and therefore, we can write that this value is actually arc tan of constant divided by sigma F average, because tau st into this, there it is a constant parameter that experimentally has been found out. Okay. So, if we get a value of this, okay, any value that is a constant, that into that divided by the sigma F average, this will be the actually angle of friction. Beta is the friction angle. Now, what it says is that the mean angle of friction is mainly dependent on the mean normal stress on the tool face. Why we call it as a model, all right, and what it says, the model solves something, predicts something, right. See, what it says is that basically angle of friction is nothing but the it depends on only the average coefficient, average stress. All these things are immaterial now, all right. This explains the following fact: as working normal rake increases, working normal rake we are talking about in case of oblique cutting, okay, and the tool is oblique, let us say tool is inclined or with respect to the velocity vector at an angle. The component of the resultant tool force normal to the tool face will decrease. Okay, grab that point. What we are saying is the working rake is increasing, therefore, the normal force will be decreased, all right, and therefore, the mean normal stress will decrease as well, because the normal force is decreasing, and the friction angle will increase. Okay. So, this has a very important, this conclusion is very important conclusion, and this conclusion you can make actually out of this final expression. That final expression comes from here only. and fortunately, because that LST and LF, their ratio, you can see that why it remains constant. This also reasonably understood. It can be understood. For example, this is constant, all right. LST and LF ratio, that is constant, because whenever if LFT is increasing, LST will decrease in the sense, okay. So that their ratio will be constant. So therefore, this is reasonably okay to assume that this remains constant. Therefore, you can get actually to this conclusion, all right. And the whole thing is called the Zores model. See, you understand in one word that what we are telling is, what is important in this model is that here, you know, this mu is different, mu is variable, it does not remain constant. In case of orthogonal cutting, all the time we are telling that the mu remains constant all along this contact length, all right. But actually this mu does not remain constant. So, you understand that we are now trying to contradict the orthogonal models, that orthogonal model actually is not right. Not right because of this, okay. See, now we have this model has shown that how to calculate the mean coefficient of friction, because it is varying. Here it is something, here it is something. So, what you take is actually this, okay, this, and this has a very close relationship with the friction angle, obviously, because this actually these two parameters are related, okay. So, this is the significance of this model. Now, let us come to that oblique cutting, okay. So, what we said is that the tool is tilted. All the complications come from this factor, that the tool is not straight, not perpendicular to the velocity vector, but it is inclined at certain angle, let us say I. So, that I is the angle of inclination. It is also called the angle of obliquity, because it is the oblique cutting, all right. And this is what happens with the forces. Those forces you have seen, right, so simple, right. It is a parallelepiped and you have the 3 forces, and you have here what happens in oblique cutting, the resultant force R is not in the plane perpendicular to the workpiece, as it happens in the case of orthogonal cutting, okay. So, I mean finished surface. So, that is, then the forces to be considered are 3 forces basically. One is the thrust force, okay. Another is the FF. FF is equivalent to FC, we said, right, earlier we said FC, cutting force, okay, and FR, all right. FC, okay, it is given here. FC is parallel with the VC, this is the one, okay, this is the cutting force. Perpendicular to the finished surface is the FQ, this is the thrust force, okay. You understand, perpendicular to the finished surface, all right. This is a sketch, this sketch is bigger here, this is a sketch, this is showing the tool, and this is the side view of this, that is perpendicular to this, perpendicular to the cutting edge. Along this is the view here, that you understand. Let me explain this diagram first. Yes, if this is the front view of the tool, then you take a section along the normal to the cutting edge. This is the cutting edge, okay. Cutting edge is inclined with respect to the x axis with an angle of I, that is what we said. This is the direction which is perpendicular to the cutting velocity vector, okay. Now, if this is the cutting edge, take a section perpendicular to the cutting edge and look at it, how it looks like. This is the sectional view of the tool, all right. Now, this is the force, okay, FQ, this will be perpendicular to the finished surface, all right. Perpendicular to the both of them will be FR, okay. FR is perpendicular to the FP and FQ will be here in this direction, right. In this view, FQ will be perpendicular, FC will be here, FP, and then perpendicular to both will be FR. Okay. So, these three forces will be considering in the oblique cutting, all right. The shear force, some other explanation in this diagram. We have taken two more views. One is the true view of the shear plane. Okay. Now, where is the shear plane? Shear plane you cannot actually see here, all right. Shear plane, if we look at the shear plane as if we are looking at it, this will how it will look. This will how it will look. Okay. And the rake face, if you see the true view of the rake face, this is how it will how it will look. Meaning that in the shear plane, this is the cutting edge, and this is the cutting edge in the rake face. Okay. All right. Now, there are certain assumptions, of course. We are saying that the tool is sharp and no rubbing or plowing forces act on the tool tip. These are not non-realistic assumptions. Okay. Here these assumptions are quite realistic in the sense, you see what we are saying is that there is no rubbing or plowing forces. One thing, stress distribution on the shear plane are uniform, okay, and the resultant R on the chip and the shear plane is equal, opposite and collinear to the force acting on the chip at the rake face. We will come to that one by one. Now, as for orthogonal cutting, the resultant force can be considered to act as two component on the shear plane, Fs along the shear plane, okay, and Fn which will be perpendicular to this. It is not visible here, it is perpendicular. So, these two forces will be on the shear plane, Fs and Fn perpendicular to that at this point, all right, and two components on the rake face, okay, F perpendicular to the cutting edge and normal to the cutting edge, which is not visible at this point, okay, perpendicular to that, perpendicular to F will be the normal force. Okay. The shear force Fs is inclined to the normal to the cutting edge. This is the normal to the cutting edge at an angle of nu s. Okay. The shear force Fs is inclined at an angle nu s to the normal to the cutting edge in the shear plane. See, this is the one, this is the line which is normal to the cutting edge, and between the Fs is along the Vs, Vc, cutting velocity. There is an angle of nu s. Similarly, the friction force F is inclined at an angle nu c, okay, to the normal to the cutting edge. All right. I have everywhere putting the diagram so that you have so that you could understand. So, the resultant force will be obviously these three forces we have taken. Okay. So, the root over of F peak square cutting force, Fp and Fc. I told you that these are the same. Initially you have taken Fc, now it will be coming as Fp. So, this is the cutting force, thrust force Fq perpendicular to the work surface, okay, and the Fr square. Fr is perpendicular to both Fp and the Fq. Once again, Fp is the cutting force. So, this will be equal to Fp prime square plus Fq prime square plus Fr prime square, because since this is a thrust force will be also perpendicular to the surface, and therefore Fq and Fq prime will be the same. Okay, Fq and Fq prime will be the same. Fp and Fr both are making the same angle of I with the Fp prime and the Fr prime. All right. So, therefore, Fp and Fp prime will be the same. So, therefore, this can be written as root over Fp primes plus Fq prime square plus Fr prime square. All right. Now, the direction of the shear force, that means given by this angle, this can be found out by tan of the nu s equal to, sorry, we will take it from here, tan of the nu, yes, tan of the nu s, this is the fr prime divided by fs prime. Okay. Fr prime we are taking from here, no, this one fr prime, it is a nu c, fr prime we will be taking as f prime, okay, and the tan nu c, all right, and fs prime we can find out from this. This is the same as the Merchant's diagram, you see this, that means tan nu s, this we are finding out with this triangle. From here we are converting them to from this, because it is fr prime is here, all right, and fs prime we are taking from here. Fs prime is equal to, like in the case of Merchant's fs was, if you remember, r cos of phi plus lambda minus alpha. This is only the normal force, because this is the diagram which is, this is the view or cross section which is along the normal to the cutting edge. So, therefore, all those things will be n, sorry, all those things are n, all right. Now, the Fs shear force on the shear plane, this is given by K into As. K is the tau S equivalent to K, meaning that this is the shear strength, okay, and As is the area. So, As we have seen as the Bt divided by sin phi n into the cos I. Tell you why. This is the shear plane, you are taking the area of the shear plane, right. Now, the area of the shear plane here, this portion will be B by cos I, okay, and this portion from here to here, it is T by sin phi n. Look at the diagram prior to that, it is a geometry. We have done that in case of the orthogonal case as the T by sin phi, remember. So, here what we are getting is the T by sin phi n, and this portion will be B by cos I. So, therefore, the area will be this into this, which is Bt by sin phi into cos I. Okay. This will give you, if you simplify that here, so that Fp can be expressed, Fp is that. So, if you take this diagram, all right, if you take this diagram, now extend that, and this can be given as Fp, we are writing as OA plus AB, okay. Now, you find out geometrically what will be OA value from this triangle what will be the AB value, sum them up, and you will find out that Fp, that is the cutting force, will be equal to Fp prime cos I plus Fr prime sin I, and it is coming from the straight geometry, okay. Here, if you look at this, this is the diagram, okay, same diagram in here. If you see that, I have simply extended it. This is the Fr prime, which is the parallel to this. This is the Fr, which is parallel here. That's all. Now, Fp prime here, okay, this is the Fp prime. Now, Fp prime is what? This is the cutting force in the normal plane. Okay, Fp is the cutting force, and Fp prime we are saying this is the cutting force in the normal plane or normal cutting force. Okay, this Fp, this is the Fp. This is like Merchant circle diagram, if you remember. This is exactly like Merchant circle diagram with this as the diameter, and if you make a circle, all the tips will be lying on the periphery of that circle. Okay. So, Fp prime will be r prime cos of lambda minus alpha in the normal, alpha n, lambda n and alpha n. So, it will be of this nature, okay, because r prime, this can be taken as the what is that, Fs prime, sorry, Fs prime into this, okay, that will be r, Fs prime into divided by this, is equal to r prime. So, therefore, we are converting that. This is the f s prime. Now, f r prime similarly, f r prime will be in the other this thing here, f r prime. This is f s and the sign of this nu s, and from this triangle you can find out the value of the f p through this, all right, because since the f r prime is this, so the f p, okay, now we can say that this is f s prime and this one, because we are putting this value in here. Okay. Mind it, because f p is given by this, we have said already here, f p is this. So, find out the value of the f p prime and the f r prime, multiply each of them by, I mean this one by cos I and sin I, and you will get this value. Okay. And we found out these values here. This is a simple algebra, all right, or whatever you call it. Now, the f s prime is f s and the cos nu s. Okay. This is coming from the geometry here. Therefore, the f p can be modified, because the f s prime can be put in here, f s common put in here. So, the f s is the k into a s, all right, area into the stress, shear stress. So, therefore, this, and then you put this value of the f s, you find this, and the remaining is the same. Okay. Now, we are simplifying by multiplying with the cos I getting cancelled here, and this in the third bracket becomes like this. Okay. This is the simplification. Now, cos nu s, by trigonometry we know that cos x equal to 1 by root over 1 plus tan square x, right. So, we can write this, all right. Now, I will remind you that the direction of shear force, if you remember in the beginning, we said that it is given by tan nu s equal to this, and it was the formula, right. You remember, we have derived that in the very beginning. I have just depicted it here. In place of tan nu s, you put this value, get this. Okay. This you simplify, and you will get this expression. So, finally, what you are getting is that the f p, if you put the cos nu s value there, it will be this one, k b t cos nu s divided by sin phi n, right. So, cos nu s we are putting this value. So, this is the final form of the f p. Okay, this is the cutting force. Does it ring any bell to you? We have done, you might be thinking that this is very something, a lot of things are there. Doesn't it ring any bell to you? If I say that we have done f c, that is cutting force in the orthogonal case, in the just we have done before lunch. Okay. It was, I will tell you, k b t cos lambda minus alpha divided by sin phi n into cos of phi n plus lambda n minus alpha n. Okay. That was the expression. If you can see that, you can check. What I try to say here is that because of that simple inclination of the tool, all right, what you are getting is additionally these factors. Okay. And of course, these factors will be in the normal plane, nothing else changed. See this, as I said that in case of f c in the orthogonal case, this is the case, it will be cos of this divided by cos of phi n plus lambda n minus alpha n. Okay. Let me show it to you. You may think that I am goofing. Just 1 minute. Yeah, look at it here. Okay. We have simplified also, right? somewhere. No, this is the value. So, what I said is Wt, that was somewhere we are taking B, somewhere we are taking W, do not mind. This one and divided by cos of this and cos of this, cos of beta minus alpha divided by cos of phi plus beta minus alpha. This is very similar to the one that we are now getting, right. Only thing is that of course this is because we are having in the normal plane, so we have to take care of that, and because of this it is coming out to be in this way, all right. So, this is one component, that is parallel to the VC. Now, we have two more components. One is that perpendicular to the workpiece surface, that is FQ, and then FR, which is perpendicular to both.
Okay, Choudhury, if I just may.
Yeah.
So, will you talk about how we get all these different angles in the next slides?
No, angles, I will tell.
I just want to make one point.
I will tell. Just give me one moment. I will just come to that phi n probably. Okay.
Yeah,
Yeah.
to address phi,
Mhm.
but if you want to talk about it, so I'll come back to that.
Okay. After that, you can add.
Use that coefficient, which is just here.
Mhm.
I'll wait for
You can add after that. I mean, when I talk about that phi n, after that you can add it. Okay. So, similarly, very similar to this, we have two more components. One is that FQ, all right, and one is the FR. If you see the geometry the way I have explained it for the first case, FC, that is FP, similarly FQ can be given in this way, okay, and FR, which is this, can be formulated, and it will be found out like this. They are very similar, you will see, obviously, okay. Now, about the angles, we have seen that all those things are based on various angles, okay. Actually 5 angles if you see this. Now, the basic angles in the oblique cutting will be the rake angle, ground and the rake face of the tool, all right, and the angle of inclination, or as I said, that is called the angle of obliquity, okay. Now, in the oblique cutting, the rake angle may be measured in more than one plane. If you remember, before lunch I told you that the chip flows at an inclined side to the normal to the cutting edge, to that side where the resistance is less, if you remember, okay. So, because of that, the rake angle may be measured in more than one plane. So, basically we have the 3 different rake angles, meaning that same rake angle by definition measured in different planes, okay. Basically the rake angle is measured, as I said, this is the angle between the rake face and a line perpendicular to the cutting velocity vector, okay. If it is measured normal to the cutting edge in a plane, this is called the normal rake angle, alpha n. That is the angle between the rake face and a line perpendicular to the cutting velocity vector. In a plane normal to the cutting edge will be normal rake angle, all right. Now, if the same angle is measured in a plane parallel to the cutting velocity and normal to the machined surface, that will be called as the velocity rake angle, okay. I am coming to those planes after this, I will explain how they are measured. Same angle, if it is measured in a plane containing both cutting velocity and the chip velocity vectors, this will be called as the effective rake angle, third one, okay. There are 2 more angles which are to be talked about. One is the inclination angle I, and one is the chip flow angle, okay. Now, the angle of inclination we said, that is between the cutting edge and a normal to the cutting velocity vector, and the chip flow angle will be angle between the chip flow velocity and the normal to the cutting edge, that will be in the plane of the rake face, okay. Now, you see the angles. Suppose we represent the tool in this way. This is the cutting edge, okay. This is the cutting edge, this is the edge tool, okay, wedged tool that I have shown you in the before lunch. Now, from here we will take the this is the top view or whatever you call it. I mean, this is the projection. This view is the projection of this. That means this is the point here, this is the point here, and so on. Okay? You understand what I say? If you look from the top, you will see this. This is the projection of this. Okay. Now, if you take, so here it is the cutting edge. All right. Here, if you take a perpendicular to the cutting edge and take a view, this will how it will look like. Now, this is perpendicular, this is in the perpendicular, along the perpendicular to the cutting edge. So, therefore, this is called the normal view, and the rake angle will be normal rake angle. All right. If you take the side view here, that means this you extend that, this point extend, this point you extend, this point you extend, that means YY. Okay. YY view is the view which is parallel to the cutting velocity. Cutting velocity is here, right? So, a section parallel to the cutting velocity will look like this. Okay. How to make it? You just project these points, y, right? So, this point here, this D point here, this point here, and so on. Project them. Okay. Now, this is the rake face. All right. You take a true view of the rake face, you will find this. That means, as if you are looking at this from here, looking at the rake face from here, you will get a true view of the rake face. This is the cutting edge. Okay. And now, if you have the chip flow velocity, to show the chip flow velocity, as we said, the chip does not flow in the xz plane. It flows at an angle to the yy, right? Let us say this is the chip flow velocity vector. It is not flowing perpendicular to the cutting edge. Once again I am reminding you, because it is oblique cutting. So, therefore, chip flows at an angle with the normal to the cutting edge. This angle is the angle of obliquity. This is I, or this is I. Okay. Now, this you project in here. This is the chip velocity vector, chip flow velocity vector. Now, let us say this is A, okay. This is B. They are both coinciding at in here, in this view, A and B, because this is a projection. Let us say in the chip flow velocity, this is E and this is F. So, E and F both will merge in here, right? A will be here. Okay? You are with me, right? I am showing you all these points. Now, this along this chip velocity vector, if you take a cross section, you will find this view. Okay. Take a cross section here along this chip flow velocity vector, that is AE or AF, like this, and show it here. You will see this. It will be revealed. What is revealed is the chip flow velocity vector, because it is there, and here the VC was perpendicular, right? This is VC. So, in this it will be perpendicular. Here it will be revealed, right? So, this is cutting velocity vector, this is chip flow velocity vector. Now, this is chip flow velocity vector means this is also the rake face, right? That is parallel to the rake face, chip flow velocity vector, right? Okay. So, this is the entire sectional views, all the sectional views, where all the 5 angles that we said, 3 rake angles, angle of inclination, and the chip flow angle will be revealed. Is it clear? Okay. Now, let us see that how they are related. I am repeating this. Okay. Now, you go along with the section, if you have understood that. Okay, one thing that I would like to say is that now I will confirm the angles. Okay. Now come back to that. Normal rake angle is an angle between the rake face and a line perpendicular to the cutting velocity vector in a plane normal to the cutting edge. Okay. This is an angle between a line, okay, between a rake face and a line perpendicular to the cutting velocity vector in a plane perpendicular to the cutting edge, right. So, this is called the normal rake angle. Okay. If the angle between the rake face and a line perpendicular to the cutting velocity vector is taken in a plane parallel to VC and perpendicular to the work surface, this is called the velocity rake angle. Okay. This is called the velocity rake angle. All right. If the same angle between the rake face and a line perpendicular to the cutting velocity vector is taken in a plane where both VCH and the VC are there, it is called the effective rake angle. You will not find any other sectional view or any other section where both these vectors will be there. So, therefore, we have deliberately taken a cross sectional view along the VCH so that VC can be revealed, which is perpendicular to VCH in this section, all right, and the VCH will be revealed because along that we are taking the section. Okay. So, these three we have said. Now, the angle of inclination is here, as we said, all right. This is the angle between the cutting edge and a normal to the cutting velocity vector, okay, I, all right. Chief flow angle is the angle between the chief flow velocity, okay, and the normal to the cutting edge, chief flow velocity and a normal to the cutting edge. Cutting edge is here, normal to the cutting edge in the plane of the rake face. This is the true view of the rake face. So, this is the nu C. These are the 5 angles that we have. These are the major 5 angles that come in the oblique cutting, all right. And these 5 angles we have seen in the forces, right. So, if you know those how to find it out, that will help you in finding out the forces. This is how you can find out actually. They are related to each other, like this I will not go to details this thing, geometry you can find out. The sign of alpha E is here. So, this is by geometry Fe by Ae. So, that Fe and Ae you now take in the projections. Okay. You take in the projections, these are all details given. There is simple algebra or geometry or coordinate geometry, whatever you call it. And finally, what you find out is that sine of the effective rake angle is sine of inclination angle, sine of chief flow angle product plus the product of cos of I, cos of nu C and the sine of alpha n. What I mean to say is that if you know one angle, you will find out the other angles. Okay. Some of these angles will be known, some of these angles will be found out from the relationship between them. Similarly, from the tan of alpha v is the velocity rake angle. From here you can find out that if it is dB by AB, then you project these, okay, find this out and you can find out that this is tan alpha v is equal to tan alpha n by cos I. Okay. Angle here, the shear angle phi n. If you remember, in the case of orthogonal cutting we said that there is a shear plane. Okay. Like in case of orthogonal cutting, here also you will have a shear plane. That shear plane will be in front of the tool tip arising from there, all right. And the direction, that is the phi n, it is in the normal plane. Normal plane is the plane which is taken perpendicular to the cutting edge, all right. So, if you take in the normal plane, here I am giving an example. Suppose this is the work motion. So then the tool is inclined at an angle of I. This is the cutting edge. All right. So here the along the OA, if you take the view, that will be the normal view. That means along the perpendicular to the cutting edge. All right. So in this view, this is the alpha n, this is the phi n, this is the uncut thickness, and this is the chip thickness. All right. So similar to that, you will find out that similar to the orthogonal cutting, we can find out the tan of phi n. I am not using the same geometry, exactly the same process, exactly the same formula. Only thing is that now the alpha becomes alpha n, phi becomes phi n, that is it, and the T by Tc remains the same, okay, because that is the chip thickness ratio which falls between 0.5 and 0.6, that is what it was told, right. Okay, now the velocity relationship here I should touch upon, because this is an important issue. For the thin shear plane model particularly, there are 3 and only 3 velocities: cutting velocity, shear velocity, and the chip velocity. Okay. Like if you see this diagram, all right, this is the shear velocity, right. This is the cutting velocity parallel to that, and this is the chip velocity, so parallel to this, all right. Now this angle that we have shown, this is the alpha E, effective rake angle, because here you have both VCH and the VC. So therefore the angle that has to be measured here will be effective rake angle, and therefore this is the alpha E, all right. Now if you take the find out the angles, here it is the phi, so it will be only effective shear plane angle, phi E. This is the angle which is alpha E, right, because this is alpha E, all right. Now this is therefore 90 minus alpha E, and this angle will be 90 minus phi E minus alpha E. Use the sine rule, all right. Vs divided by this, as we have done that in one of the velocity relationship, okay, and you will find that the shear velocity through the cutting velocity can be given through this formula. Here the phi will be known, alpha will be known, okay. Similarly, the chip velocity vector through the cutting velocity vector can be found out this way, all right. Now here one thing I should clarify, that why this diagram will come into picture. Like we are saying VCH is equal to VC plus Vs. Why so? Obviously the chip can flow if we have the shear and the cutting, right. So the result of the cutting velocity and the shear velocity is that chip flow. So therefore VCH is equal to VC plus Vs, right. So therefore if it is this, that means these 3 velocity vectors have to be in the same plane, okay, and if it is on the same plane, that means that is the plane where alpha E will be measured, effective rake angle will be measured, right. That is all. I think that will clarify all those things, that we have the angles, we have the oblique cutting forces, and now we will have some discussion, okay. So if you have some questions, suggestion.
To explain oblique geometry, it takes years to understand it. So don't think that in 1.5 hours you will become an expert. But the idea of this is to give you some idea that things are complicated. And in reality, everything is oblique. Orthogonal is just ideal case to try and understand what things happen, how things happen. Things are actually more complicated than even this equation shows you here. So, but what we can do is we can simplify things, so which is what I will try and do. Cutting coefficients, right. So, you can see this is the FP is what you call the feed force. You call this the feed force? This is, so I don't know your terminology. So, this is the chip is forming. This is your uncut chip thickness, what you call T1, I believe. Okay, this is your clearance, and you call this gamma. Yeah. Yeah, but what do you call this gamma? You call this alpha? This is gamma. Okay, because I use different terminology, but that doesn't matter. Can everybody see this? Yeah? So this is your tool. Yeah? This is your workpiece. Yeah? Now, this is oblique. Yeah? This is orthogonal, very straightforward. What you can see, there is phi n, which is your shear angle, yeah? But the oblique shear angle. Yeah? This is phi n. Yeah? There is gamma is your rake angle, clearance angle.
This is friction angle.
This is friction angle.
Yes.
Okay. This is your normal rake angle. This is your chip flow angle. Okay. So you can see there's a lot of angles. Yeah? Most of which we don't know.
Five.
Yeah, 5. And if you know one, you can derive the others, like Dr. Choudhury said. But we still don't know this shear angle. Yeah? And
That we have determined through the T1 by T2.
yes, so one way is you determine the chip ratio. Yeah? So you get T1, T1 by T2, where this is T2, right? Yeah? So you get this ratio, and from that you can get the chip thickness ratio, and from that you can predict shear angle. But getting this chip thickness experimentally is very difficult. Yeah? How do you? Yeah? We had a little discussion with some people after the lunch break as to how to get this ratio. And one way is you do these quick stop experiments that you spoke about, yeah? Where you stop the experiment in the middle and you either measure the shear angle, that you put a grid onto the things like Dr. Choudhury showed, or you try and get something of a ratio like this. Now, because you're cutting and the chip is flowing, yeah, measuring the deformed chip thickness is very difficult. So what we instead normally do is we measure volume of the chip. Yeah? Because you have material, you know what material you're cutting, you know the density. Yeah? And if you know the volume, from the volume you can back calculate what T1 should be. So the width is in the plane. Yeah? So the width of cut we know. Yeah? No, because we are assuming that flow does not take place on the sides. Yeah? So it's only along this. So there is not too much flow outside the plane of the board, yeah, or outside the plane of cutting. So you know the width, yeah, and you know length of the chip, yeah, and you want to calculate T. So what you want to get is volume, yeah, is T into, what do you call width? You call it AW or something? W into length. Yeah? We can get W and L, yeah? And we know that, I'll come that side. Yeah? We know that density rho is mass upon volume. Right? Density we know of the material. Volume we want to calculate T. Mass we know, we can measure the chip. Yeah? So from this you can get what T1 is. Yeah? So this is how you can calculate the chip ratio. This is easy in orthogonal cutting. How will you do this in oblique? Yeah? So in oblique cutting, if you want to get, when you have all these angles, you really can't get this so straightforward. Yeah? You really can't measure the chip length. You can't even sometimes measure the chip width because things flow, and getting this ratio is very difficult. So what we instead do is we get something we call cutting coefficients, yeah? Or some of you might know it as specific cutting energies. Have you heard of this concept before? Yeah. So the question is, how do you get this, yeah? And what is this value? So let's look at this equation. Yeah? And instead of writing it so in this form, I will write this differently. Fp is the feed force.
FP is the cutting force.
So this is Fp. Or what do you call this? Which one is yours? Fp.
Oh, FP is the cutting force there.
FP. So feed force, no? This is
It's a cutting force vertical to the tool. Your tool is in a different direction. So it will be normal.
hmm?
No, don't make it that way. You make it the way another vertical. I mean perpendicular to the cutting edge. Take the section. That.
No. Let's assume orthogonal cutting. Your FP is your feed force or is thrust force?
Cutting force.
Thrust force.
Cutting.
Yeah, but cutting force has got components, right? So what do you mean?
Cutting force is vertical to the tool tip.
Okay. Anyway,
It's very confusing.
so what happens is we all grow up in different terminologies.
You
Yeah.
use your terminal. That will
Okay.
be easier for you.
Yes. So I'll call this.
You simply say what it is.
I'll call this FT. This is a thrust force on the tool, and this is a feed force, yeah, or FF. Yeah? We call this FF. So now we know FF and FT, yeah? Two forces acting at the tool point. Let's try and rewrite this in terms of that. Yeah? Okay. So what you can do is you can write FP is something called K. Yeah? We'll call this PC, a constant, yeah? Times your B is your chip width, yeah? And T is your
Cutting width of cut.
and T is your chip thickness. Yeah? Okay. Instead of writing that complicated equation, you can say that this specific cutting energy or coefficient is equal to this term here. You understanding? Yeah?
Divided the same.
Yes. So as in this entire term, this term as well as K here is your shear stress, right? So what I want you to remember is this form, because we will not be using this. This is very difficult to use. What we will use is something of this nature. This is assuming there is no rubbing. In reality, there is always rubbing. Yeah? So even when there is no cutting, yeah, the tool is in contact with the workpiece surface and it is always rubbing the surface. So let's try that on the other side actually. This is getting in the middle.
Now if you want to lift it up, right? You want
No, let it be. Yeah. So this is your chip that is forming. Okay, this is your T1, right? T1. Okay, so if I assume there is no cutting, yeah, so no depth of cut or no chip thickness, so that means that is only rubbing. So this nose is always in contact. Yeah, is everybody following? So what will happen there? Your force will become, let's say Ft will become KTC BH plus KTE B, where KTE, where this term is because of rubbing. There is no chip thickness here. There is no T. I call this H. Yeah? Here there is H. Yeah? H is the chip thickness. B is your width of cut. KTC is this nice fancy coefficient which has got all these parameters inside. So this form of the equation becomes very easy to remember. Now this is valid for thrust force, for feed force as well as axial force. Yeah? Is the edge coefficient or rubbing coefficient. Yeah?
Your rubbing means it's similar to plowing, right?
Rubbing is plowing. Rubbing is plowing. So when there is no cutting, the tool, if for example you run the tool with zero depth of cut but in contact with the workpiece, it is rubbing. Yeah?
See, if you remember, we said in the assumption that there is no rubbing or plowing. So that rubbing or plowing gives rise to the KTE factor.
Okay.
So this is the formula when you take this and realize that there is a rubbing. So you find this.
Okay. So this becomes very important to remember. Remembering this is very difficult. Deriving itself is very difficult. Yeah? But what we can do is we can lump everything inside a coefficient. And how we get these coefficients is a different matter. For example, if I equate KT to this term multiplied by shear stress divided by sine of your shear angle. Yeah? if I can get this coefficient somehow, I can predict what your shear angle will be. Otherwise, I don't know what it's going to be. So the way we get this coefficient, we'll talk about tomorrow. We will also experimentally identify these coefficients. On the machine, we'll do turning as well as milling. But point was, I just wanted you to remember this, because this is the form that we most normally use. Yeah? Any questions about this? Yes, go ahead. Dr. Choudhury, there's a question for you.
Yeah. So
How can you figure out the exponent y in this model?
Exponent y. That's a constant.
So how can
That
you
is empirically found.
experiment?
Experiment. Okay. Any more questions? So please, we have few more minutes before we go for the tea.
So I have a lame question, sir. So why does T1 and T2 arise at all? I thought it should be the same.
Oh, so what you're doing in cutting, yeah, is there is a shear, and after shearing, you're deforming the material. So the material is flowing. Yeah, T1 is when it is inside the work wall, as in inside bulk, and T2 is when it is deformed. So after deforming, it is flowing,
Kind
right?
of rolled out.
Yeah, so it flows.
Yes,
Material
twice,
flows.
almost twice more.
So material flows and it separates. Yeah? Oh.
50 to 60% more. That's why this ratio
Yeah.
coming out to be 0.5, 0.6.
And this ratio you can determine. It changes with tool, it changes with cutting conditions,
right.
it changes with
Material,
workpiece
everything.
material.
Yes, yes.
Aluminium will flow more.
Continuous chip flow. How will we decide the length of chip? Because it's a continuous process.
Oh, the chip has to break. Yeah? Otherwise, you don't know length. Yeah?
Then the forces will increase.
Yes. Yeah. So that's why I said even determining experimentally the chip thickness ratio is very difficult. It works mostly for orthogonal cutting. The experiments we normally conduct, yeah, is to get KTC, these coefficients, because this has more information than that ratio. So what you want to get experimentally is this, and this we'll do tomorrow, yeah, and we'll talk about how we do it. Because you're right, if the chip is flowing, you can never get length. Yeah? Where do you stop it? And those experiments need to be very carefully designed. If anybody has tried, yeah, it's very difficult.
Somewhere material property also been taken care.
This is like a golden number, you know, KTC. Yeah?
K itself is that. K itself is inside.
ये जो है ना,
KTC
because
includes K.
yeah, इसका जो shear stress है is inside this. You're right. Huh?
Like hardness.
It's all inside this.
No, this is strength. It is the shear strength which is taken into account. Shear strength, yes.
So let me write this again. Maybe it's not clear.
Overall strength of material. Strength of material.
Johnson Cook. As in to get shear stress, you can use that. Yeah?
Yeah.
You can predict. We won't go into that. Yeah? So FT. Let me write this again. Yeah? Is KTC BH KTE B. Yeah? Okay. KTC is a function of shear stress and geometry.
Including angle.
Yeah, that's what I mean, geometry. So you can see it's a function of material as well as tool geometry.
I mean hardness it comes into picture.
Yeah, it's inside shear stress.
Yes, yes. Can be.
As in, it's a material property, right? Hardness. What you want to do is get this coefficient. One way to get shear stress, as in there are models like you said. Yeah? There's a Johnson Cook model,
It's a function of strain,
strain hardening, and temperature.
So hardening will come in strain rate.
And temperature also. There is a Hall patch effect, another model, which relates stress to hardness and grain size. So, as in there are models to predict shear stress as a function of different material properties. But one way is to predict it, but that's is never going to be accurate because you still need some constants which are experimentally determined. How will you get shear angle? Yeah? To predict forces, you still need shear angle. Even if you get the shear stress from a model, how will you get shear angle? So what we are saying instead is perhaps you can lump everything inside into this one nice coefficient. It's got hardness, it's got shear strength, it's got whether it's dry cutting conditions or wet, tool geometry ke effect, everything is inside this one lumped coefficient. And this is valid only for the cutting conditions that you will identify it with. We will do this tomorrow, and we'll talk about how to do this tomorrow. Well, any other questions?
When you can measure the length, can you not measure T1, T2 also?
Like we said, yeah, it flows. And measuring that chip thickness, have you seen? You've seen chips.
Yeah.
Yeah. Where do you measure chip thickness? Yeah. Because it changes even across the section.
Even along 40 mm, 30 mm.
Oh, 2 millimeter. You talk 40 millimeters is too much. Yes. That's why it's a very small sections that we measure. Yeah. You can try tomorrow. We'll give you a vernier caliper. We'll give you a chip. You try and measure the chip thickness for us. Yeah.
Yes.
Probably
In
we
that
never
case,
done that
whenever
till
you
now.
get a-
So you can try it. Yeah.
if you want to do that, if you want to do it experimentally, you have to take a segment which will be straight, find out the length, measure the weight, and do it the way that it was shown.
And that is again very difficult. So what we're instead saying, let's use a
See,
different
another
approach.
thing is that the other side of the chip, this is not plane, so you can't measure it also. You can't measure it properly because it will be all with the undulations. Yes, undulations.
Now what we'll do tomorrow is we'll give a vernier caliper to you.
We'll go to the lab in the afternoon and we will do the exercise.